happens to the cloud. So find the arc length of x equals t squared plus 1, y equals 4t cubed minus 1 over the interval of 0 to 1. Right? So you'll find that when we we derived the formula for arc length, that was pretty challenging, but actually putting the formula to use is really not too difficult at all. Right? We do need the derivatives of x and t, dx dt, and we need dy dt with respect to t, which is good because there will be instances where we have to take the derivative with respect to other variables. That's a different story altogether. Right? So t squared plus 1 becomes 2t, and 4t cubed minus 1. Got a little congested over here, so I'll take that as a typo, the spacing. If anybody needs typo bonus points, which early on in the semester, pretty much everybody does. So that's something. And again, just as a reminder, because I know sometimes people miss the first class, sometimes people just miss that portion of the introduction. When I point out typos, or if you find typos, any kind of mistake, all you have to do is send me an email detailing what the typo is. And if it's not obvious, just tell me how to fix it. Yeah, for grammar, definitely tell me how to fix it, because if I made the mistake to begin with, odds are I thought it was the right thing to do, unless it's something really obvious. Or if I point it out in class, you could just say typo number 4, page 3. You send that to me in an email. If you're the first one to make the submission, then I give you a bonus point. And I put it on Blackboard. The thing is, I generally, rude as this may seem, I don't reply, because what happens is, I usually get like 20 or so. Well, this is a smaller class, but like 10 or so typos, submissions per person at minimum per night. If I reply to all of them, I'll be up all night. So what I do is I ask you, just be patient, and the next day, 2 days later, just have a look on Blackboard. If you got the bonus credit, then you're good. If you didn't get the bonus credit, somebody beat you to it. Right? I'm very honest when it comes to that sort of thing. It's not like I'm going to take your typo and not give you credit for it. Right? If you're the first one, you'll get the credit. Right? And so far, I've gotten a bunch of submissions. Some folks have racked up a ton of points already, so the points are there for you to earn. Right? So that was the quick aside, but it was worth talking about. Right? So if we want the arc length, we're going to use S equals the integral over the interval of a to b. I'll write the formula first, and then we'll hop into it. Of dx dt squared. I'm going to turn off my line draw. Oh, I actually did, though. It's weird. Why did that happen? Plus dy dt squared dt. Right. So it's really just a matter of saying, okay, I got my 2t. That's going to get squared. And my 12t squared is also going to get squared. Right. That's all going to happen under the radical. And it's all going to be related to the integral. So let me just get all the other trimmings there. Going to happen over the interval of 0 to 1. So then, easier said than done. The only thing that we have left to do is integrate this. All right. So we could simplify. I mean, sometimes it's worth it to do that, because maybe it's something that you could do quickly and easily by hand. Maybe that's the case. So let's give it a look. So we're looking at 4t squared plus 144 t to the 4th under the radical over the interval of 0 to 1 dt. All right. Now we have a common factor of 4t squared that can be pulled out. If you pull out a radical 4t squared, I'll write it. I'll show the intermediate step. We have 4t squared. That's going to become a 2t. That's going to leave us with a 1 plus 36 t squared over the interval of 0 to 1 dt. Right. So cleaning up further, comes 2t. One plus, everything else is going to be the same. You don't really need all these equal signs. I just put it in there. It felt a little naked without it. All right. So this is what I really have to integrate. And it's really just a matter of saying, okay, well, what's the appropriate integration technique? Looks like use substitution. I mean, there's other ways, but this is the most reasonable way. So we'd have du is equal to 72 t dt. I fully understand that there are different schools of thought on use substitution. I do it a particular way. It may or may not be the same as the way that you learned it in the past. I'm also going to show you how you could have done all this on the calculator. The reason why I'm going over this now is because I know that people often need a little brush up on their integral technique. So in my mind, it's worth taking a couple of minutes to go through it. You might find it to be a waste. If so, that's fine. You get to relax for a minute. If you know all your integral rules, good for you. All right. So what I want to do is I want to make this allow me to cancel this out. Okay, that's the whole point. Okay, because the u is going to take care of the 1 plus 36t squared. Okay, so if I want this to be in terms of u, strictly in terms of u, then I would have to make that correction. So what I'll do is I'll multiply both sides by 1 over 36. All right, and so that actually creates a cleaner substitution of 1 over 36 du corresponding to 2t dt. So that allows me to do a direct substitution, replacing the 2t dt with a 1 over 36 du. All right, the only thing that we'd have to handle there would be the bounds. And hopefully this is something that's pretty consistent no matter who you had for Calc 1, Calc 2. It probably told you the same thing. You have a choice. You can either convert the bounds over into the units of u. They're in units of t at this point, but if you want to, you can convert them over to the bounds to units of u, or you can work the integral and then bring the bounds in later on after you've reversed substituted. All right. It really doesn't make much of a difference either way. It's all going to come out in a wash. All right. So I continue my process here. I'm going to go without the bounds. I'm going to leave them. I'm going to leave it boundless, and I'm going to write this as 1 over 36 radical u, or quality everything. Not much better. All right. And that's going to be du at the end. Right, so the u came from the 1 plus 36t squared substituting, and the 2t dt became 1 over 36 du. So then I could say 1 over 36 u to the 1/2 du, integrate that. So increase the exponent by 1, you know the deal. So 3/2. So we're multiplying 2/3 by 1 over 36. So if you multiply 2/3 by that, it's 1 over 54, I think. All right, and that would be, well, that's the thing, like over the interval of what to what? Well, it would be over the interval of u of 0 to u of 1. It's just, I'm not going to work with that. I'm going to convert it back into t notation before making my substitution. All right. So that allows me to work in terms of t rather than the u's. So 1 over 54, 1 plus 36 t squared to the 3/2, and that's going to be over 0 to 1. The idea being that I would prefer to work with 0 and 1 as opposed to if I plugged in a 0 and a 1, well, the low bound would have been fine, but on the upper bound I get a 37. That wouldn't be pretty. And so, you know, it's apples and oranges, I guess. You can think of it a bunch of different ways. It's up to you. I'm pretty sure that 54 is right. You'll let me know if I'm wrong. All right, so then I make my substitutions. I'm going to pop in a 1. That's the easy part. Well, actually, they're both pretty easy. So 1 over 54. Plug in the 1, you're looking at 37 to the 3/2 minus 1 over 54. Then it would be 36 to the 3/2. I didn't really give myself enough room here, so I'm going to clean it up. And then move some things over here. Now the 36 to the 3/2 we could actually do something with, but then it kind of begs the question of like, to what end? You know, what's the benefit? Because 36 to the 3/2 will be equal, I think, to 216 because the square root of 36 is 6. 6 cubed, I believe, is 216. But then 216 simplified with a 54, I'm not really going to be able to do anything with that 37 aside from going to decimal form. So then it kind of begs the question, all right, well, if we got to go to decimal form here, why couldn't we go to decimal form way back when? And the answer to that is you could have, right? It all depends on what the question is asking you to do in terms of a final answer. But I'll get it. Go ahead.
Yeah, just a question. If we change t with 0, how did we got 36?
Oh, sorry, it should have been a 1. Thank you. Good call. So this would cancel away. Very good. Yeah, for whatever reason in my brain, I replaced the 1 with a 0 instead of the 36 with a 0. I don't even know that. So that's the closest I can come up with in terms of an excuse. So yeah, so that 216 would have even been irrelevant. All right, so it looks like we're, aside, you know, other mistakes aside, it looks like we're getting something about 4.2-ish.
Professor?
Yeah.
I have 2 questions. So
Sure.
First of all, if we are putting it in decimal form, is there a certain decimal place you want us to round out to, or does it not really matter?
It doesn't really matter as long as, I mean, if you choose to round it a certain way, just make sure you round it that way correctly.
Okay.
You know, so if you decide to go to nearest 100th, make sure you do that correctly.
Okay. And then also, are we allowed to like take, like, for instance, that third step that you have on the left, the square root of 4t squared plus 144t to the 4th, and just plug that into the calculator?
Yeah, that's actually what I was going to go over next, because
okay.
yeah, generally whenever we're coming up with a decimal answer, it's always going to be acceptable for us to use a calculator approach. And so that's really the point of what I'm about to get to. Right. So
okay, so we don't have to show that we know how to integrate that, right?
Correct. I mean, there will be some instances down the line where we're going to have to integrate in general terms. So that's why I took the time here to go over the process.
Right. Okay. Got it. Thank you.
No problem. Yeah, so folks, as a general rule of thumb, numerical answers you can integrate any way you want, whether it's with technology or by hand. But when we tackle some of the curvature concepts, when we get to multivariable, it involves that. I don't know how much of this you remember, but the fundamental theorem of calculus, we just applied part of it, the first part, where you substitute in the 1, you substitute in the 0, and go from there. But there's the second part where we talk about differentiating an integral, right? We're going to need to be able to handle some integration techniques in order to be able to tackle those ideas. So bottom line is, if a final answer calls for a number of any kind, you can use the calculator. And I'll be pretty, I was going to say pretty clear. I'll be very clear on the test what questions you need to do by hand and which ones you don't. As a general rule of thumb. So I guess this whole conversation is about general rule of thumbs. rules of thumb. There's generally only one question on any test where you would ever need to do it by hand. All right, so if you keep that in mind, it's going to come down to your setup. After that, it's a matter of just knowing how to do it using technology. All right, so it's kind of like a double jeopardy thing. I'm not a big fan of you've already been assessed on your ability to do all this integration stuff in Calc 2. I don't want to have to ding you for those skills yet again. So probably more explanation than you needed, but I figured I would kind of hit that point home. All right, anyway, so let's get it into the calculator and see if I did it right. Well, that's kind of fun, except when I screw it up. So functions, if you go under miscellaneous, it's weird how it's miscellaneous. I don't know why. They just throw in all the calculus stuff at the end, but you can see the integration symbol is there. You can also see a summation, all that good stuff. It's weird because the symbol in the menu doesn't have bounds, so you might think that it's something like a indefinite integral, but it's actually a definite integral. It just I guess they didn't have the wherewithal to put little tiny boxes next to it, but whatever. So 0 to 1. So you could tap or click into each of the open fields there, but I find that if you use the left and right arrow, that kind of gets you where to go, where you want to go. So let me just show you again. So I'm in the bottom field. I put in the 0. I hit the right arrow. That puts me where the integrand would be. And if I hit the left arrow again, it puts me on the top. Just so I don't have to worry about getting my fat finger to fit in that little tiny square. That's a me thing though. You want to put parentheses. You want to open up a set of parentheses for your integrand. In this case, the least simplified form of your integrand is what you want to put in. That's not always necessarily the most important thing, I guess, but the reason why, let me just get out of my own way here. The reason why I'm saying to do that is because, you've seen me do it. You make a mistake in algebra, yeah, you simplified it a little bit, but what you put in is an incorrect integrand. And so you get an incorrect answer. The least simplified one is most likely to be the most correct one, unless you're really confident with your algebra, which is possible. But why take the chance? Now, you could use X instead of T. I kind of want to make it look nice. So I'm going to use T's, but you can use X's if you want, as long as you're consistent. The 12t squared, then close it up to indicate that you are now done writing your integrand, and then throw your dt at the end there, and then you're good. All right, so 2t squared plus the 12t squared again, then close up the integrand. So parentheses to start the integrand and parentheses to end integrand, slap on a dt at the end, and you'll get it, in this case, 4 point. Oh, it really shouldn't be 4.2, huh? Now that I look at it, it should be 4.1. After I made this whole thing about whatever method you choose to use, make sure you do it right. I went and didn't do it right. Classic Bob. Except my name's not Bob, so that doesn't even make any sense. All right, so yeah, 4.1, 4.15, just not 4.2. Play it safe, round it to 4. It doesn't really make much of a difference. When you're not given any context, we're not going to lose any sleep over rounding. When you're given the context, generally, you just think of any word problem you've ever been given in the past. They usually have rounding instructions, so just be mindful of that kind of thing. All right, number 5, find the arc length. If x is equal to t sine t plus and y is equal to t cosine t, so we got a little work ahead of us. Dx dt. the little product rule here. So first times the derivative of the second, cosine of t, plus the second function, which is the sine of t, times the derivative of the first, which is just a 1, so I'll leave that off. dy dt, first times the derivative of the second, plus the second times the derivative of the first. So, same deal. The derivative of t is equal to 1, so we don't really need that. Right. Now, this might be kind of a bear to type in, but you sort of look at it, pros and cons, risk reward, however you think of such things. And this is happening over 0 to 1, same as before. What's going to be harder? Simplifying a little bit and typing it in, simplifying a little bit and integrating by hand, not simplifying at all, but typing it in. And the other, not simplifying, I mean, you can't do it by hand unless you simplify. So the next possibility wouldn't make any sense, right? So it makes sense to give it a little bit of a look in terms of simplifying before you type it in. But you obviously don't want to spend too much time doing that, because once you spend, more than a couple minutes on that, you could have already typed the problem in and gotten a more reasonable answer, or an answer quickly. So t cosine t plus sine of t, we're going to square that. Negative t sine t plus cosine t, we're going to square that. And then dt at the end. All right, so it'd take a little doing to type it in, but it wouldn't be too terrible. But let's take a look. Let's see if maybe through simplifying we can make it a little bit more palatable. So t squared cosine squared t plus 2t sine t cosine t plus sine squared t. It's like, yeah, let's just type it in, right? Give it another second. Let's see what happens. I'm going to write, and I'll use my highlighter tool here. So I got my product here. That corresponds with this expansion. I'm going to get my product here, and I'm going to put that expansion right below it. All right, just so everybody is on the same page here. So t squared sine squared t. Now we're going to have minus 2t sine t cosine t plus cosine squared t. So all this is getting added together. All right, now this is just side work, so I'm not going to put the radical over it, because I've had people in the past say, well, is that a fraction now? Well, it's not. It's just a little bit of side work, right? But I like stacking it this way because I think it becomes a whole lot easier to see what the relationships are. If there are any cancellations, it becomes a little bit more apparent. Like, for example, these two are exact opposites. We got a Pythagorean identity here, and kind of a Pythagorean identity over here. All right. It'll actually turn out that it'll involve a Pythagorean identity, but we got to do a little bit more work to get there. All right. So for this guy, I can factor out a t squared. And we'll have cosine squared t plus sine squared t. And then for this one, that's just a 1. All right, that's our Pythagorean identity. So it actually cleans up really, really nicely, because this is just going to be t squared plus 1 under the radical. All right, because cosine squared t plus sine squared t is equal to 1. You want to put the little strike through, a little 1 there, you can. So we're actually integrating a much simpler expression over the interval of 0 to 1. All right, so we could pop that in as opposed to that nasty expression that we started with. I mean, you may be starting to get a handle on my personality enough to know that I'm about to type in that big nasty expression anyway. But it's definitely worth it to simplify in this case. So we're looking at about 1.1-ish. This time I do believe I rounded correctly, hopefully. So try something else here. 0 to 1, open parens, open radical, open parens again, t, cosine, t, got parens everywhere. Close the paren for cosine, plus sine t, close the paren for sine, close the paren for the radicand, and square it. Then plus open paren, negative t, sine t, close it up for the sine, plus cosine t, close it up for the cosine, close it up for that part of the radicand, square it, step out of the radical, close it up for the integrand, and pop on a dt. And I think that might be the first time I've ever gotten that right on the first try. Usually I type in something incorrectly. As it turns out, I got the same decimal. So it either means I screwed up both of them in a way that got me the same answer, or I did it correct. All right. So obviously it takes a lot more of a painstaking approach, but you can get there. And honestly, I don't know. I don't know what the right way is, because I look at this and I say, well, the algebra didn't seem too bad, but you make a mistake in the algebra, it's all over. All right. Those trig relationships and the distribution process. Or you can screw it up typing it in. Bottom line is, the type of mistake that's going to occur for a problem like this is most likely going to be of the quote unquote careless variety. Now, if we wanted to integrate this by hand, I really don't have the heart to do this to you by now, but it does, or at least right now, it does involve trigonometric substitution in order to simplify. So it's a little bit of a beast. And I've in the past killed an entire class period working on a problem like this. So I'm gonna table it for another time. But yeah, there is a way of doing it by hand. It's not the hardest problem you'll ever see, but like I said before, if we're looking for a numerical answer, the calculator approach is perfectly reasonable. Right. So that's that. Now let's take a look at areas and arc length in a polar plane. Right. So just something to keep in mind, or hopefully you've had an opportunity to look through the Unit P stuff, and if you haven't, it's because you're pretty strong with your polar coordinates. Polar coordinates are always in the form of r comma theta. So basically, instead of x's and y's, we have r's and thetas. So it just begs the question of, okay, well, we know that using rectangular coordinates and parametric coordinates, parametric equations, I should say, that we can do a whole lot of things related to the calculus of, anything happening in the plane. So we could find extrema, we could find arc lengths, we could find areas, Those are all things that can happen. We can find volumes if we expand it into a third dimension. All right, we'll get there, but for now we're just kind of living with plane regions. So it begs the question, all right, how does this tie over or connect with polar coordinates? And you know, it's not too bad. It takes a little doing, but it's not too bad. All right, but it does rely on a pre-calc concept, and that is the area of a sector. Now, specifically, it's a circular sector, but everything is implied to be circular in the polar coordinate system. So I didn't think that was necessarily right. So area of a sector, in general, if area is equal to 1/2 r squared theta. Right, now, if you look at the formula below, area within a polar graph, you have over the interval of alpha to beta or a to b, if you want to make a difference. We have something very similar, 1/2 r squared d theta, right? And the idea comes down to the fact that, yeah, okay, I'll be the first to say that this is definitely not a circle, and it's not a sector of a circle. But every little line segment, quote unquote line segment, little tiny little piece here can be a portion of a much larger circle, right? So I can use my line draw tool to do something like, oh, okay, well, that didn't work out as planned. Trying to hit the edge. Better, kind of. It's kind of oblate. It didn't really pan out. Let me see if I can rotate it a little bit. Oh, that's why. Let me just get a circle. Do it the old-fashioned way, and then match it up. There we go. So that little tiny, teensy tiny little segment, just this little guy, I'll use a highlighter here to make it really pop. Not too much highlighter. That little tiny bit is an arc in this gigantic circle. You know, the less curvy an arc is, the bigger the circle. You know, it's kind of like when you walk outside. You're walking on a big giant circle, little sphere, but if you're walking on a straight line around that sphere, it'll feel linear, but you know that it's circular. Right? It's the same idea here. The larger the radius, the less of a curvy nature the circumference has. Right? So just this little piece, this little guy right here, I'll shade it in, can be determined based off of this circle that's given to us. All right. So if what I did was I found the area of that little tiny sector from that circle, and then let's say, for example, let me go red, try to eyeball it also. Oh, no. I mean, I guess it's good that it recognizes ellipses now, but it used to not, and I liked it better that way. Well, I need the radius to be at the center, or the center of the circle. It's gonna be a little too thick. It really doesn't matter. Just do it that way. All right, so got a little bit of a section over here, sector, right on that end. Same idea. So what I would be able to do is, with a bunch of different circles, I could fill in that shaded region and then add them all up and get the area of that shaded region. You know, but that's pretty arduous. What we can do instead is use a variable polar equation right? It's kind of like a polar equation that has variable radius, you know. So you think about a circle, something that's circular, but its radius varies depending on where you are in terms of theta, right? So what this is saying is, all right, well, instead of doing all that, why not work with the original polar equation, right? So we allow for the equation to be variable. Let R vary according to theta, and then move in infinitesimal steps of theta. I'll say tiny because infinitesimal is a big word. All right, and move in tiny theta steps, infinitesimal theta steps. All right, so what I'll do here, let me just kind of hide this for a second. Put it over here for a second. I'm going to duplicate this. And then I can bring all this stuff back. All right, so what we would be doing is taking a little tiny step, then a little tiny additional step, and then another tiny step, and so on until we've covered the entire field. All right, and so we would be looking at those little teensy tiny steps being related to theta. All right, but if they're tiny, we would call it d theta. All right, so we could find all of those little radii based off of, or all of the radii based off of whatever the function is, because r represents radius, right? And it'll be dependent not on theta itself, but on the little teensy tiny movement in theta, right? And that would give us what we need in order to, span that region, right? So this function here, this red arbitrary curve, is going to be specific to whatever r is. All right. So that's a little bit of a taste of the concept. I mean, I didn't really get into a proof or anything, but that's just giving you a little bit of the gist of it, because I didn't want to jump into a formula without at least telling you the why. I'm not big on that. And then the arc length of a polar graph, that's a little bit of a different story. We'll get to that in a little while. That has to do with direct substitution into the rectangular arc length formula, right? So that might even be a side video, because I generally don't ask students to reproduce that on an assessment, right? So we'll come back to that, but that's a different formula, a different concept, right? So let's tackle an example or two related to the area of the sector, and you see what we're up against. All right. So first thing is sketch the figures. Now, since I mean, I'm operating under the assumption that if people needed to, they had to look at the unit P. They said, you know what, I'm a little iffy on that polar coordinate stuff, so let me have a look at that. But I got to imagine some people didn't. But I'm not gonna insult the people who spent the time by reteaching all that stuff. So all I'm going to do is just give you the sort of a bridge version, right? Where it says sketch the figures. One thing I said in that video, and I'll kind of re-emphasize this throughout the course, I'm not really big, even if the class was in person, I'm not really big on making people sketch graphs to give credit for the act of sketching a graph. I feel like that's sophomoric, There's a class for that. I don't think I don't think this is it. You know, so a sketch of a graph could simply be a Desmos graph, right? Generally, I'm not going to ask you to make a graph very often, and if I do, a Desmos graph submission is perfectly acceptable, right? So to get it into polar form, you hit that little wrench, tap on that grid that looks like a polar grid. Make sure you're in the right domain. Right here it says -10 to 10 for x and -8.5 to 8.5 for y. I don't really care about that as much as I care about the radians degrees part of it. Right, you'll see each of the domains here are in 0 to 2 pi, or r 0 to 2 pi. That's a radian measure. So unless you want to think of everything in terms of degrees, I would say keep it in radians, make sure it's in radians, and then go from there. Now, the theta step on the top, that's more for people who are TI calculator folks. But if I haven't sold you on the Desmos calculator as opposed to TI-84, I don't know that I ever will, especially after this lesson. Because I could just type in r equals 3, and it gives me the graph, and I'm done. No additional steps are required. All right. I can also indicate what I want my domain to be without having to hit window and all that stuff. The step here, it asked for the step, I gave it the step. All right, that step is just to indicate what the values that we're going by on the scale, the sliding scale ought to be. All right, but that's irrelevant because in this case, it's 3 no matter what, because it's a defined function where r is equal to 3. So theta step isn't really relevant in this case. All right, now this is very clearly a circle. It's very clear that the radius is equal to 3. So they're asking us to find the bounded region. And by bounded region, I mean the area of the bounded region. I said that so emphatically, but I missed a word. Yeah, so, okay, cool. Well, if this weren't a calculus class, you'd already be done with the problem. By the time I was finished labbing, you'd probably finished the first couple of problems. And the problem is, it is a calculus class, specifically Calc 3, indicating that we'd have to use the techniques associated with polar coordinates. Sorry, I was just blabbing on to buy myself some time to get the screenshot. All right, so done, save to files. Oh, not save to files, save to photos, yeah, schlemiel. Not that I needed to save it, I just want to have it for I like to have it in my camera roll in case I want to use the picture again. All right, so there's my sketch. That's great. I did so good. Look at that perfect circle I drew by hand without any assistance from technology. Yeah, that's the idea. All right, so we already know that the answer ought to be 9 pi. But let's do it using the Calc 3 approach. And for the record, it's not really a Calc 3 approach. It's just general calculus of polar coordinates, right? So it's not limited to just Calc. So area is going to be equal to 1/2 over the interval of a to b, alpha, beta, a to b, 0 to 2 pi, 1/2 r squared d theta. All right. So over the interval of 0 to 2 pi, 1/2, well, r is equal to 3, constant, 3 squared d theta. Now, one thing that you should verify is related to the domain, and that is that the graph does exist. Oops. I mistook this for a slider related to the domain. I'll address that in a minute. But you should verify that that entire domain is required for the one full turn around the circle, right? Because if you have multiple turns around the circle, you might accidentally double count the area. All right, we'll see examples of that in a few minutes. My writing here is terrible. Oops. It's always terrible. I know. All right, so 9 halves theta over the interval where theta is going from 0 to 2 pi, All right. Now, I'm kind of glossing over the procedure here in the integration process. And the reason why I'm doing that is because we're integrating with respect to theta, but it's no different from integrating with respect to x or y or whatever. Right? As long as your bounds of integration, let me go with green here for those keeping score at home. Your bounds of integration are consistent with your integration variable, then you use ordinary integration techniques. Right? So in this case, it's just increase the exponent by 1, divide by the new exponent. However, there was no variable there, which implied that we really had a theta to the 0th power. So hence the arrival of the theta. So we're looking at 9/2 times 2 pi minus 9/2 times 0, result 9 pi, which is what we expected to be the case to begin with. Right? So that's good news. It means that we did it right. All right. Now, you might ask, you might wonder, I would wonder, wait, do we have to do it this way on the test? If we could just use the area of a circle formula? And my answer to that is, well, it depends. If it's a multiple choice type question, I don't care how you do it, as long as you show valid work. Right? Valid work usually implies the title of the course. You know, so we've got calculus in the title, so you should show some calculus in your solution, right? But if it's multiple choice, I'm not really looking for, I'm not looking at your work too carefully. It's when it's a designated free response question, meaning something that's, you know, show all work. That's when I'm looking for all those details. So the idea behind a multiple choice question is it's supposed to kind of be a freebie. Right, I throw a bunch of those in unit tests. I want you to have some free points along the way, because I'm going to make up for that with the questions that are much more challenging. Right, so it kind of balances things out. Right? The second example, r equals r sub I. Right, r sub I is indicating some constant value dependent on some unknown position within a sequence. Bottom line is r is equal to some number, all right, but it's unknown, so we're thinking of it as a constant, just an unknown constant, all right. Fortunately, we're going to pretty much use the same process, right, except that our diagram is, you know, it's variable, right. So the area here, 0 to 2 pi, 1/2 again r squared d theta. But this time, we can't replace the r with a number other than some unknown constant. So I would say 0 to 2 pi, 1/2 r sub I squared d theta. Right, increase the exponent by 1, divide by a new exponent. Oh, actually, sorry, it's constant. So 1/2 r sub I squared theta over the interval of 0 to 2 pi. Okay. So this is constant. All right. The only way it would be variable is if it had a theta in it, and it doesn't. Right. Or at least a relevant variable. This is kind of like a teaser for partial integrations. That may not mean a whole heck of a lot to most of you, but maybe some of you. Right, so we're looking at 1/2 r sub I squared over the interval. Oh, sorry, I already did that. Two pi minus, replace the theta with a 0. So if you simplify this, you're going to get pi r sub I squared. Okay. So what we're, you know, it was a little choppier than I would have intended, would have liked, but it gets us there. And so it's telling us that the area is dependent, it follows the model of pi times whatever the radius is numerically squared, right, which is what we know as the area of the circle formula. So it's kind of like a partial derivation of the area of the circle. It's just a little something. Right, but it's kind of the teaser to get us into the real stuff. Right, because in number 3 we talk about the area contained within this not a circle polar graph. Right? Now it's still going to be circular, but it's not going to be a circle. So there's that, and then there's also the fact that you know that 0 to 2 pi may be one full turn, it may be half a turn. There's a lot going on there, so we have some work to do. Right, so we could still follow the model of area being equal to integral over a to b, or alpha to beta if you like, r squared d theta. We can do our substitution. I still don't know. I'm going to hang on. I'm going to hold off is what I meant to say on that 0 to 2 pi. I'm so tight on that. I'm going to leave it boundless for a second. I'm going to put the 2 plus 4 cosine theta squared in there, d theta, and see what's going on here, because I don't know if I necessarily need to do all of 0 to 2 pi, and also I don't even know what this looks like yet. I mean, if you did the UniP packet, you would know that this is a Lima sum, but that's kind of beside the point at this point. Right, so r is equal to 2 plus 4 times the cosine of theta. Now to get theta, just type in theta. There's other ways, but this is the quickest and easiest way. When you type in theta, the full word, it converts it over to theta because it knows that that's what you want. Right, now what I do is I put, and it's entirely up to you if you want to do it this way, but what I'll do is I'll put in a lower bound of a and an upper bound of b. Or at least I normally would, except for whatever reason it's not letting me do that this time. I don't know why. Did I use A and B already? Yeah, I don't know. That's so strange. All right, well, I'll just leave the 2 pi here, and then I'll just kind of dial it back a little bit just to make sure that I have, I don't know why that's not working. Let me just try something real quick. I wonder if when I spelled theta wrong initially, it got confused. No, it's still, maybe I'm just misremembering.
Would it
Maybe.
be because A and B are undefined or not?
Well, that's the thing. It was going to be defined as in the form of a slider in a second. I just don't know why it didn't do that. All right, well, I'll figure it out later. Maybe I'm just misremembering. Maybe it's the kind of thing that only works in the world of functions or rectangular coordinates. It's not as important. It would have been nice if it worked though. So 0 to 2 pi would be, it looks like one full loop, but I'm not really 100% sure, but I need to be 100% sure. So what I'll do is I'll just dial back from 6.28, 2 pi, approximately 6.28. I'll dial it back to like 6.2, but not 26.2 for crying out loud, 6.2. And you see that it's almost there. It's almost one full complete turn. So what I'll do is I'll make it 6.27. And you see that there's a little gap there still. So 6.28 is pretty close to one full complete turn with 2 pi actually closing the gap. All right, so without getting into the algebra behind it, because there's other ways to handle this. What you can do is you can solve, make it, solve an equation to determine when the polar graph is at, what is that? It looks like it's at 6. You know, set it equal to 6 and solve. But this is a pretty quick and easy way to make sure that you're not overshooting one full turn. All right. It's a little nicer with the sliders. Let me try 2 other values. Yeah, even with S, okay, whatever. I don't know. Maybe it is something that only works in rectangular. I'll research it later. So that tells me that my 0 to 2 pi would be fine as bounds for one full turn. But the issue that we're going to run into here is that we're going to run into a lot of issues, but not the least of which is actually integrating this thing. But if I want to, let's say, go from 0 to 2 pi, what's going to happen? Let me just get this diagram in here, because hand waving isn't going to get the job done. Copy, save that, and so let me just kind of take you through a few theta values at a time. So that's why I wanted my slider to work. Let's say I went from 0 to pi over 6. All right, so that gives me a little bit. So I'm starting 0 to pi over 6. Gets me from here, well, to about right here, pi over 6. Let me make it a little bit curvier. All right, but what's really happening is we're accounting for all the little areas, all the little sector areas on that interval. If I can draw. No, it's not going to let me get that little one in there. All right, we'll just freehand this one. Looks terrible. All right, so that's 0 to pi over 6. Now let me do the pi over 3. Gets me even further. All right, so I can go even further. It's going to get me over here. All right, it's the same idea. I'm gaining more in terms of area. All of this stuff. All right, so let me try pi over 2. Pi over 2 is going to get me right to the axis.
Professor, why don't you just do pi?
Well, I'm trying to show the progression.
Okay.
So as I continue on, I'm getting more and more. I'm getting more and more area. All right. So then, you know, we can go even further. Well, I'm at pi over 2. So let me say 3 pi over 4. All right. 3 pi over 4 kind of overshoots it a little bit. So maybe, or at least a pole. So let me do 2 pi over 3. 2 pi over 3 gets me back to the pole. All right. So that's going to give me, going to give me all of this and a little tiny bit of stuff going on in there. So now I have really the whole top half accounted for. So on the interval of 0 to 2 pi over 3. All right. But now let's take a look. And by the way, it's reasonable to assume that if we went from, and so here's my 0, that gets me to 2 pi over 3. If I want the same angular movement, but the other way, it's reasonable to assume that I would cover the bottom half. All right. So this would also be negative 2 pi over 3. All right. Same idea. I would be building outward, but in the opposite direction. I get all, oh, that looks terrible. I get all of this area accounted for on the bottom end. If I went from 0 to negative 2 pi over 3. Right, it's out of the domain, but we know that negative 2 pi over 3 is the same as 4 pi over 3. All right, but then the big question would be, well, what happens if I continue, into the realm between 2 pi over 3 and 4 pi over 3. Like, for example, I guess, like we said before, I said before, 3 pi over 4. All right, that'll get us a little bit into this loop. Let me get a bright color here. I'm going to go with an orange here for those who go home. So 3 pi over 4 would get us over here. That's going to cover, that's going to account for some of this area. Then maybe I go to 5 pi over 6. That's going to get me even further. It's getting down over there. Maybe we do go to that pi. If I go to pi, that's going to get me all the way over here, including the measure of pi itself. And then we could go even further and go all the way up to 4 pi over 3. So let's say 7 pi over 6. That'll get me up over here. Uh, 5 pi over 4. That gets me over here. And then the rest of the way would get me, if I went to 4 pi over 3, that would get me the whole inner loop, right? So if we account for that area between 2 pi over 3 and 4 pi over 3, that would just give us the inner loop. So area from theta equals 2 pi over 3 to 4 pi over 3 gives inner loop. All right, so what we can't do is go from 0 to 2 pi, because what's going to happen is we'll go all the way around, grab that inner loop, and then go all the way, go the rest of the way. So what'll happen is, let me use the highlighter to really demonstrate that. We would start here. We would get all of this area on the top half. All of this stuff would be accounted for, including the inner loop. All right. Then we would go into the inner loop and count all that stuff again before picking up the bottom half of that inner loop on the return trip. So bottom line is, long story short, after all that, we can't go from 0 to 2 pi, because if we do, we're going to double count that inner loop. So what we need to do is go from 0 to 2 pi over 3 of all this stuff. And then add to that whatever we would get by going from 4 pi over 3 to 2 pi, skipping over the 2 pi over 3 to 4 pi over 3. Or we can go from 0 to 2 pi directly, but then we'd have to subtract the 2 pi over 3 to 4 pi over 3 interval, right? So it isn't quite as simple, or it's nowhere near as simple as the previous cases where it's just a matter of where does it start, where does it stop? You got that inner loop that's going to be double counted if we're not careful. All right. Now, if we were to distribute this out, we would get something that would be integrable, but the problem is we'd have to use a trigonometric substitution. It wouldn't be terrible, but it's not something we want to do. All right. So this is straight up calculator work, unless it's something you want to do. But like I said, I'll get you with enough instances later on in the course where you have to do something by hand, where just do it in the calculator for now and enjoy these moments while they last, because they'll be gone before you know it. All right. So 0, 2 pi over 3. Now, I've already defined R as 2 plus 4 cosine theta. So what I'm going to do is I'm going to type in 1/2 R squared d theta. So it'll spit out that value for me, all right, which is good news. All right, now, if you recognize the symmetry of it, you realize that you don't really have to do the second computation. You just double this one. right? So, but let's say you don't recognize that, use the duplication. That's the thing. You sometimes don't recognize things because you can do it a different way and everything's fine. All right, so 4 pi over 3 go into 2 pi. I gotta get there though. Same value. So it's really just a matter of saying, okay, well, I never really needed this one, so let me just double the previous one. So we're talking about approximately 35.5-ish. All right. Now let me just show you really quickly. And by the way, that only works because we defined what R was. We could have done that before, and I'll show you that in a second anyway. Let me show you what you would have gotten if you went from 0 to 2 pi. All right. So not so wildly different. And in fact, that difference from 37.7 and the 35.5, which is the correct answer, is only attributable to the area of that tiny little loop on the inside, right? So that inner loop has an area of about 2-ish, a little less than 2, maybe 1.8, right? But let me just show you really quickly. If we had gone back to that good old R equals 3, right, you look at this and say, well, we got 9 pi. What's that? Well, 9 times 3 is 27. So this is a little bit more than that. Good bet that this is 9 pi. So it works, right? So what we just kind of arrived at here is a calculator that can be saved to give you quick and relatively easy computations of the area contained within a polar function, right? So what you would do if I were you, I would save this baby. I would just title it area of a polar graph and have it ready to go, and then maybe put in a little note here. Pop in a little note saying input polar equation for R. And then if you really want to get snazzy with it, indicate that the integral below area contained between the function and the pole over A to B. Something like that. You can spice it up any way you want, but then you're reminding yourself that anytime you type in something here for R, that's going to change the integral. And you'd also have to remind yourself that the theta values are going to be dependent on particular circumstances. All right. I'm just going to call a quick timeout here. So number 4, again, sketch the graph, sketch the figures, then find the area between the polar graphs. So it's a little bit more in the realm of funkiness, but definitely doable. All right. So it's just a question of the approach that you want to use, because if you look at the previous page, there's a formula. The formula, I think, I hate to use the term common sense because I feel like somebody is bound to get insulted by that, but that's usually what it comes down to. It's like, well, you're finding the area of the one figure and subtracting from it the area of the other if you're looking for the area in between the two, right? So we could kind of go by that, or you can use the formula on the previous page. It's entirely up to you. But one thing that we do need to make sure is the case is that there is consistency within the domains for the two functions, right? The two polar equations. All right, so I'm going to save this. This would be area of polar equations. Yeah, it's kind of weird. You'll hear me go back and forth between saying functions and equations when it comes to polar coordinates. It's kind of one of those weird circumstances where you've been trained to think of a function in a certain way. You know, it's like, oh, it passes the vertical line test. I would beg the question, what's a vertical line in polar coordinates? You know, so it's going to be another polar equation. So the vertical line test doesn't apply here, right? It has to do with input output, right? So as long as you don't get more than one output for a single input, you're dealing with something that's a function. Right? That's why we're looking at theta predicting r rather than the other way around. Because if you look at, for example, the equation of a circle, if I were to have r as the independent variable, I'd be looking at r predicting the value of theta. We'd have infinitely many possible thetas that depend on the value of r. But the other way around, I can tell you that if theta is this, then r is that, right? And it's a one-to-one relationship, right? So that's what we're looking for. Now, in the case of these two equations, again, it's to say, oh, actually, I didn't really need to do that. What I can do is just take this one and just bring it on down, because that's 3. So that's one of them. And then I could just look at the other one, square root 9 cosine 2 theta. Theta. Fat finger strike again. All right, so what we're looking at here looks like an infinity symbol, but we do need to verify that it's one full loop in that 0 to 2 pi domain. All right. So what I'll do is I'll just dial back my 2 pi. Words. I'll make it, like I said, 2.7, 6.7 is what I should say. 6.27, if I can get a friggin' sentence out without screwing some part of it up. Right, instead of 6.28, and just verify that it's coming just a smidge short of one full loop, right? By zooming in, you know, a lot, we can verify it, all right? And then just make sure that dialing that up to 2 pi closes the loop, and it does, all right? What we're often going to run into is the fact that what we have is too much in terms of domain, where they'll say go from 0 to 2 pi, but that'll give you 2 turns around the figure. So far, that hasn't been the case, but we'll cross that bridge when we get to it. All right, so this is going to end up being overlapped upon the other function, but let me get them side by side first. I'm going to get a reasonably consistent scale going. Copy. Just dial it down a little bit. So these are the 2 equations. And now I'm going to just plot them side by side. Not side by side, concurrently. I already plotted them side by side. All right. So we have a few different approaches that we can take here to come up with this area I can get rid of. One would be to figure out, because I want the area in between, we can figure out the area corresponding to this figure, if my pen works. Get all this area and subtract from the area of the circle. The benefit of that is that we already know the area of the circle, and even if we didn't, we could figure it out pretty easily. Okay, so the area here is 9 pi. All right. So if I subtract the two, so 9 pi minus whatever this one is, then I'll have it. All right. I could do that way, or I could use the formula. Now, what I said before about, just remembering what the title of the course is we want there to be calculus in here somewhere. It doesn't have to be for a simple circle, right? It's kind of like a, sort of defeating the purpose. Or sometimes I call it an intelligence penalty. I don't want that ever to be the case. Something that you could reasonably figure out in your head, that you should be rewarded for that, right? So if you're able to do that. So what we'll do here, go back to purple, is figure out the area of the Spider-Man's eyes, I guess, and subtract it from the circle, and what we'll be left with is the rest of his mask. So something along those lines. So the big question would be, do I have everything I need in order to figure out the area of this whole thing? Well, we can try. It says undefined there. That's kind of a red flag. 0 to 2 pi, 1/2 r squared d theta says undefined. Okay, well, what if I only went to, let's say, pi? Well, I only grabbed half of it, say the top half. Still says undefined for the area. Oh, well, it's actually going to pi, 2 pi. But I adjust it so it goes to pi, and it still gives me undefined. All right. So let's say I only do 1/4 of it. I'm sorry, 1/4 of pi, not 1/4 of the whole thing. We're finally at a point where we get an answer, so that's something, right? 2.25. That's kind of nice. There's something there, right? But it begs the question. I mean, we can do trial and error here all day long. Oh, that's great. I got one piece of it. I can subtract, and I'm sorry, I can multiply that by 4 and be happy with this one particular problem, yet have learned nothing about the appropriate approach for getting an answer to this type of question. So let's dial it back here for a second and say, all right, well, wait a minute. There seems to be an issue if I go beyond that pi over 4, right? So let's say I go to pi over 2, it gives me undefined in terms of the actual figure. Pi over 4 and pi over 2 is giving me the same portion, and it's just a question of, okay, well, what's going on there? All right, so let's take, like I said, a step back. Now let's look at the algebra of this. So I think it's pretty safe to say that this thing, if I started off at, let's say, 0 to pi over 12, it's pretty safe to say that 0 is our origin point. We're starting, not origin as in the origin of the graph, the coordinate grid, origin as in the beginning of the figure, as in the origin story, where it began, the alpha. So it's working its way around in this fashion here, okay? So then we get to pi over 4, and that gets us to the pole, all right? Then, for whatever reason, it seems to take a break. Somewhere between pi over 4 and 2 pi, it seems like nothing's happening. So let me do like pi over 3. It's still that same piece. Pi over 2. Let's do 2 pi over 3. I guess it's still on break, which is weird. Okay, maybe 3 pi over 4. Still on break, still snoozing, I guess. Okay, let's see if we go to pi. If you go to pi, it gets the whole thing, but somewhere between 3 pi over 4 and pi, it started moving again. So let me do 5 pi over 6. So 5 pi over 6, it seems to be on the move again. It's just a question of at what point between 3 pi over 4 and 5 pi over 6 did it start moving again? Well, that's a question for algebra. All right, so one thing that we could do is take that equation, r equals the square root, poor quality square root. 9 cosine 2 theta. We could set it equal to 0, but we kind of want to do a little bit more than that because it is a radical. I only want to be focused on positive outcomes, you know, in a bunch of different ways. The value underneath that, the radicand needs to be not only 0, but greater than 0. It can't be negative. So let's look at 9 cosine. That was weird. 9 cosine 2 theta. Let's make that greater than or equal to 0. All right. So we're only focusing on values that are greater than or equal to 0. Solve cosine 2 theta greater than or equal to 0. Divide both sides by 9. That shouldn't be too difficult. All right. I can go a couple of different ways here. One way would be to convert that over using a double angle rule for cosine. Another way to do it would be to create, I call it a dummy variable. I don't really know what else to call it. But another variable that I could use to swap out the 2 theta. So for example, let C equal 2 theta or X or whatever, it doesn't matter. I'm going to use A for area. Let me say, I'll go with B. And so cosine of 2B greater than or equal to theta. But as you know, hopefully, when it comes to, just a B. When it comes to inequalities, we tend to think of it as an equal sign until we have to draw a conclusion for the final answer. So we'd want to be thinking of where this function is going to be greater than or equal to 0. Where it's going to be greater than or equal to 0. Sorry, a little cough there. I got a frog in my throat. So we can do this with good old-fashioned Euler circle trig, or we can do it by graphing the cosine function. Either way is going to be fine. It's up to you. What I'll do is I'll just open up another Desmos calculator, just so I can talk to you about the graph of the cosine function, and then also we can use unit circle. So let's say I'm doing y equals cosine of x. And we only want the parts of it that are greater than or equal to 0. When we know where y is equal to 0, that's the x-axis. So I'd be looking at these values, basically anything except for the pi over 2 to 0, right? That corresponds with the unit circle. If you think in terms of the unit circle, some of us do, some of us don't. ASTC that's that shortcut way of determining where the individual functions are positive versus negative, right? Positive or greater than or equal to 0. We know where it's equal to 0, but greater than 0 would be in the first quadrant or the fourth quadrant, right? So that's consistent with this graph because it's saying go from 0 to pi over 2. Here's 0, here's pi over 2. Skip everything from pi over 2 to 3 pi over 2. So there's 3 pi over 2. And then go the rest of the way. I guess I didn't need this max point here. Go the rest of the way to 2 pi. Kind of weird why that was showing up. Let me show the relevant ones. This one, this one, this one, and this one. I guess I'll just identify that one because even though it gets back to the x-axis after 2 pi, we stop caring about it at 2 pi. All right, bottom line is it corresponds with the unit circle. That's really all this gibberish is getting at. All right, so any value really between negative pi over 2 and pi over 2 is going to get the job done. All right, so in terms of cosine being positive. So that talks about the domain, right? So the domain would have B being in between negative pi over 2 and pi over 2. However, two things that we need to keep in mind. One is that the overall domain of the function is going from 0 to 2 pi. So I would not consider the negative pi over 2. I change that to a 0 because I can't go lower than 0 for theta. The other thing that we need to consider is the fact that, yeah, I chose to replace the 2 theta with a b for the sake of computation. But it's really, I can't just leave it as b. It really is a 2 theta. So 2 theta is between 0 and pi over 2. And so when I divide out the 2, I get 0 less than or equal to theta less than or equal to pi over 4. All right, so that's a more analytic way to come up with that little piece, the little eyelid of Spider-Man in the first quadrant, right? So all I'm going to be able to get by going from 0 to pi over 4 is this little piece here, which, as it turns out, because of symmetry, is all I really need, right? Which is good news. You want to rely on symmetry as long as you know it's definitely symmetric. Now, in the unit P packet, when you talk about all those classical curves, there are some characteristics that I go over in those videos. If it's not something that this isn't something that's familiar to you, go back and watch those. Definitely, I intended for that to be helpful, right? I don't want to. What I really want to say is it will be helpful. I think it's helpful. I just don't want to be wrong. I like to think I did a pretty decent job in making a video or a set of videos that could be helpful in understanding this stuff. But if I'm wrong, I'm sure somebody will let me know, right? So I want to find the area. I'm just only going to focus on that little eyelid, right? So going from 0 to pi over 4, 1/2 r squared. So here's my r squared d theta. All right, all of which could be chucked into the calculator. So I can go back to my other Desmos, and you'll see we're going to get to a point where we're becoming more and more proficient with working with multiple Desmos calculators at the same time. That's the idea. That's where you want to be. All right. You could say, I mean, all right, look how many I have open at any given time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I got 12 Desmos calculators open right now. Right. And for good measure, I have a GeoGebra mixed in there. You know, so that's just something to keep in mind. Now you see that little fraction icon underneath the 4 on the left-hand side? That's telling you that there's a fraction equivalent available. So if you just tap on that, it'll convert it over into fraction form. So that's giving me 9/4. That's assuming you don't recognize what the fractional equivalent is immediately. All right. So it's possible. So just, don't assume that I'm insulting your intelligence by saying that you can't convert to a fraction. Sometimes there's decimals that you look at and say, no way it's going to convert cleanly to a fraction, but yet there is a fractional equivalent, right? Now, I want the entire set of i's. I want the I part of the mask. I only got 1/4 of it. So what I'll do is I'll take this and multiply it by 4. So really what I'm looking for is not just this one integral. I'm really looking for this integral multiplied by 4, which is going to give me a clean 9. And so that tells me that the overall area of the shaded region here is going to be 9 pi minus 9. All right, so the area of the shaded. All right, gives you the area between the two. All right, I'm showing a lot more detail here probably than you would need to get full credit, or definitely than you would need to get full credit on the test, just because that analytic approach that I showed for coming up with the bounds of integration, that's only if you're not comfortable with what the graph is giving you. If you look at it and say, well, I don't really get it. I don't see, is it 0 to pi over 4? Is it 0 to pi over 2? Is it 0 to what? You know, then you need some other method. That's the method, right? That's, or at least a reasonable method. Right? There's other ways, but that's probably the best way. When it comes to graphing, this is called a lemniscate, that an infinity symbol, or the eyes of Spider-Man. When it comes to graphing it, it's really kind of strange how it sort of plays out, because you would think that, you know, I'm going to do some hand gestures here, but if you start on the right-hand side and then you get to the pole, then you would tend to go down and then back around, you know, creating an infinity symbol the way you always have, you know. So if I do it on paper, you would expect it to be something like this. Oh, geez. Well, that's why I don't do it on paper. All right. So something like this, or maybe it started on the right, on the left, and then come back. But in both cases, you're starting on one side, going through the middle, and then coming back. Right? That's the way you want to graph it. Right? With practice, it gets a little easier. The problem is, when we graph this one, you know, 0 to pi over 4, eventually we got to the sweet spot, which is 3 pi over 4. That was the end of the break period in the middle, I guess you could say. At which point we started increasing again. So then we went to 5 pi over 6. It started working its way towards pi, at which point it gave us the top half. So it's really graphing it something like this. Right? And then if I want to pick up from there, I can say, well, maybe it's going from pi to 5 pi over 4. So let me throw in a 5 pi over 4. All right, so that gets me this piece. So we're looking at something that's going around this way, around this way, and around this way. And then logically, if it's going into the pole, then it would have to come out of the pole this way. All right, there's a path of motion that's going on here that doesn't really kind of line up with the way that we would necessarily think to do things. All right, so, and that has a lot to do with why we were getting the error message when trying to do it just straight from 0 to 2 pi. All right, because if you think about rectangular coordinates, I'll also turn there for a second. You had parts of the graph that were above the axis and parts of the graph that were below the axis, the horizontal axis. If you had any part of the graph that was above the x-axis, its area was a positive measure. If it was below the x-axis, its area would be a negative measure. Right? The same idea holds true here, except there is no x-axis to be compared to. It goes in terms of counterclockwise and clockwise rotations, but specifically coming in and out of the pole. All right, so that's why it starts giving weird occurrences in terms of the areas. All right, so kind of strange in that regard, but it is what it is. So anyway, so that takes care of that. Now one more.
Professor?
Yeah.
For the one that we just did, is there a way to solve that one using the second equation from page 4 for the area between polar graphs?
Oh, yeah, well, that's the issue. Yeah, so yes, you can do it that way, except what you would be doing is using that model just only over the interval of 0 to pi over 4.
Mm-hmm.
And then once you get that little sliver, then you multiply that result by 4.
Professor, can you scroll down just a little bit so I can screenshot that?
Yeah, you got it.
Thank you.
Yeah, so you could use that other formula, except the issue ends up being that if you were to try to do it over 0 to 2 pi, you'd still have that error component going on with Desmos and even the TI calculator. TI calculators will just flat out tell you it's 0, you know, because you'd have equal parts positive and negative areas that'll cancel each other out. But when it comes to the formula itself, you just want to make sure that whatever you're using in that formula is guaranteed to be positive over the interval that you select. And so the best idea is to use the idea of symmetry and the fact that it's you're gonna have a discernible area for both parts over the interval of 0 to pi over 4. And you can subtract those two areas and then multiply the result by 4. Although you may have to go pi over 2 because pi over 4, you wouldn't have accumulated enough area to subtract the entire pedal, if I'm not mistaken. Yeah, I would try it and see if it doesn't work. You might have to go pi over 2, now that I'm thinking about it.
So how would you figure out whether to use that second equation or to take the difference between the areas?
Basically, anytime there's an issue with finding that one-to-one relationship between the two equations. So for example, in this case, pi over 2 covers a quarter of the graph for the r equals 3, but you've gotten a quarter of the graph for the pedal, for the lemniscate, after pi over 4. Because there's an inconsistency in domain, you would want to do it separately.
Oh, okay.
Yeah, it's still doable, but it ends up being more trouble than it's worth because of that whole what I was calling it is like the graph is taking a break from pi over 4 to 3 pi over 4. That throws a monkey wrench in the whole thing. That's the whole thing.
Okay. So it depends on whether or not you can make alpha and beta the same.
For the two functions, yeah.
Okay, got it.
All right, so the last one that we'll do tonight, find the area outside of 4 sine theta and inside 7 cosine theta in the first quadrant. Now, when I say quadrants, I'm referring to rectangular quadrants, but if you overlay that on the polar coordinate system, that still goes hand in hand. It still kind of covers the same region. So going from 0 to pi over 2 is what we're interested in here. All right, so here's 0, here's pi over 2. So 4 sine of theta, and again, it's just a question of whether or not you're familiar or comfortable enough with polar graphs to graph this kind of thing by hand. I don't know that too many people are, and enough to graph anything other than a straight r equals a constant solely by hand without using some sort of either a table of values or technology, right? At least not in an introductory course. All right, so this is what 4 sine theta looks like. If you remember from the unit P videos, coefficient, sine, coefficient, cosine. Those are going to give you two circular equations. One is going to be symmetric about the y-axis, the sine function. The other is going to be symmetric about the x-axis, that's the cosine function. The r value indicates the radius. I'm sorry, the diameter. All right, and by r, I don't know why I said r value, but the coefficient in front of sine represents the diameter. All right, so we just need to make sure that that 2 theta is going to give us one full turn around the circle. So like I said, I'll just dial it down, dial it back to 6.27, something like that. Make sure that it's not going to close the loop up the wrong side. I'm not seeing any gaps. So what I'll do is I'll dial it back to pi, and there you see I get a full circle there. All right. So how did I know to go pi? Two possibilities. One, this is my 40th time doing this problem, unfair to you. 2, I just made a guess. If it wasn't 2 pi, maybe it's pi. A little bit more fair. But what I would do if I were you is I'd look at it and say, okay, well, 2 pi, well, what about, okay, 6.27 wasn't showing a gap. So let me try 6. Still not showing a gap. Let me try 3 pi over 2. Oh, stepped out of the function there for a second. It's still showing a complete circle, there's no gap there. So let me dial it back to like, well, that's not. Let's say 5 pi over 4. So that's 225 degrees. Still one full circle, minimum. Let me try 7 pi over 6. And then eventually you get back to pi and you're still seeing a full circle. It isn't until you dial it back to something shorter or smaller than pi, let's say 3 pi over 4, that's when you get an incomplete circle, right? So then it begs the question, all right, well, that could take a while. Is there a better way? Well, it looks like the loop gets closed at the pole. So if I have r equals 4 sine of theta, I can just set that equal to 0 to see the instance in which it hits the pole. All right, 0 is equal to 4 sine of theta. That would be, the pole is at r equals 0, in which case sine of theta would be equal to 0. And then we just got to be thinking unit circle. Under what circumstances is the sine of theta equal to 0? That's going to happen at 0, pi, 2 pi, and so on. All right, so not a whole heck of a lot of help because 2 pi is still part of that possible solution set. But if you go from the smallest to the next smallest, well, we've already done it, but you know, you see we got one full loop, and then if you smidge it up from there, let's say instead of smidge it back from there, instead of 3.14, we say 3.1, and you can see that there's the ever so slight incomplete portion of the circle, right, indicating that, well, that we're looking pretty good in terms of our domain. Okay, so then it begs the question, and bearing in mind, of course, that we don't need this whole thing, but we do want to know when the circle begins and when it ends, right? Because then by extension, we'll know what the halfway point is, what the quarter way point is in terms of theta. So we can do the same thing for cosine. R is equal to 7 cosine theta. If I set that equal to 0 to see when that's going to hit the pole, I can say cosine of theta is equal to 0. That happens, I mean, the very first instance around the unit circle in which that happens would be pi over 2, all right? I mean, we could say negative pi over 2. They didn't give us a domain here. So I would say pi over 2, 3 pi over 2, 5 pi over 2, and so on. Well, let me take a look at the graph, r equals 7. This time, cosine of theta. So definitely a bigger circle. That's really not the important feature just at this moment. It's really just a matter of knowing when the magic's going to happen. So if I try doing 0 to, let's say, pi over 2, that gives me the top half of the circle. That's an instance in which the graph is going to be equal to 0, the first instance when it's going to be equal to 0. But does that close the loop? It doesn't look like it, because we want to be thinking about where this graph starts. So let me try 0 to pi over 4, for example. You can see here that the graph is starting at that rightmost point. So let me even bring it back further and say pi over 12, pi over 24, pi over 48. I'm just doubling. 96. All right. So as I get smaller and smaller in terms of theta, it seems to be starting off at r equals 7 units to the right of the pole. And then as I increase my theta value, so make it bigger and bigger, I'm getting, let's say, pi over 3, closer and closer to that pole until I get to pi over 2, where I've gotten to the pole. So setting it equal to 0 tells me something else in this context. It's not telling me when the loop is completed. It's telling me when I get to the pole, In this case, that happens to be half a circle. Now, I don't need much more than that, but it's useful information, right? So that tells me by extension that if I go from 0 to pi, then I'm going to get one full circle, right? Now, as it turns out, if I want to be in the first quadrant, we have r is equal to 4 sine of theta. I want that happening over 0 to pi over 2. Right? And that would actually be the same for cosine, 7 cosine of theta. Right? So if I do pi over 2 in both instances, that's going to give me the parts of the curves that are in that first quadrant. All right, so I'm restricting myself, so I'm not accounting for anything that's beyond that, which is good news. I mean, we need more information to get an answer here, but that's a good start. All right, so now what I need is the area bounded in between these two functions. All right, easier said than done, of course, but doable. Otherwise, I wouldn't be here. All right, so what we're looking for is all of this stuff here. All right, so that's what we're looking. I'm going to get rid of that shading though, because what's going to happen is we're going to have a natural transition between the two curves. All right, so I'm going to really bring this.
Professor, I'm sorry, but isn't the problem saying outside of the r equals 4 sine theta? So
Oh yeah, good call. 4 sine outside, but inside of 7 cosine. Yeah, you're right. My bad. So the question of what I intended and what I actually wrote. All right. Well. All right. So this is what we're looking for. As it'll turn out, we're going to kind of need that overlap anyway. But yeah, you are correct. That's what we're being asked. All right. So let me get rid of this. Regret doing it individually in terms of tick marks. What we're going to do first, we have the area of that entire semicircle. So the area of the green semicircle, let me get green. All right, pi r squared is what it ought to be if it were a full circle. So we're going to do 1/2 pi r squared. All right. We know that the diameter is equal to 7. So the radius is equal to 3.5 or 7/2, either way. So we're looking at the area being equal to 1/2. I'll use the 7/2 pi times 7/2 squared. All right. So 49 quarters times a half is going to be 49/8 pi. So that's going to give us the whole top half of that circle. Right? We can use calculus for that, but we'll get the calculus in a second. So it's really not 100% necessary. All right. So what we need is the area of that overlap so that I could subtract it off from that other piece. All right. So that's what we're going to do. Again, is this the way that you would necessarily think to do it yourself? I don't know. But this is a strategy that you can follow. All right. So what I'm going to do is find the area contained within this piece. Good, you can get on the appropriate interval. So it's just a question of what that interval is going to be. And that interval is going to be related to the intersection between the two curves. All right. So what I would need to know is where these two graphs intersect. So set the 4 sine of theta equal to the 7 cosine of theta. I'm looking at the clock here. kind of want to finish this problem, but I don't have the heart. Okay, well, I'll get the intersection and then that's pretty much where we'll leave it because I don't have the, I'm not one of those teachers that are like, oh, let's finish this problem, even if it takes another half hour. I'm not like that. Y equals, and just to save ourselves the algebra, we'll just find the intersection using technology. Y equals 7 cosine of theta. Oops. This needs to have a 4 in front of it. 7 cosine. I'm using x's here. Graph is a disaster. That's okay, because I only care about the interval in the 0 to 2 pi, 0 to pi over 2, I should say. So I restrict the domain. The intersection is about 1.0517. All right, so theta approximately 1.0517. We're going to use that piece of information to help us the rest of the way. But we'll leave it there because I don't, like I said, I don't want to run over time. All right, so let me stop the recording.